Thank you for everybody joining tonight's AIAA Los Angeles section distinguished lecture event. We have a very wonderful speaker and leader in aerospace and AIAA for tonight, and also happy to be back to the proper with all the aerospace icon and the history of AIAA. Proper used to be viewed as the icon of AIAA because as we chatted with Mr. Yang earlier, we have many AIAA events here, but unfortunately, Proper raised the price. So hopefully we can get back more often. Thanks to Proper, give us some discount, which will continue. So again, before we start some logistic, you already probably know where the restroom, men's room, restroom is. And the coffee on the back, and iced tea, iced water, hot tea. So today, we're so happy to. Oh, by the way, this event is being recorded. So to be aware, we just have an interesting conversation with the speaker about somebody say something in the Dodgers game, but we happen to. Yeah. Yeah, yeah. And it remind me a couple of years ago, I went to a concert and in Ohio, and they have the game World Series between the Braves and the Cleveland, and it was one of the first game or second game, and nobody was listen to the music. Of course, they listen to music, but during the intermission, they all pull out the radio for to see what's the score. But please listen to the talk today. It's very unique. Don't follow the games. You can see the result afterwards. So this is very unique and a very very special occasion. And Alabama is very happy to have the family here. Actually, I was just chatting with our speaker today. How Alabama is continue to serve everybody is by including all the people, not just used to be. Alabama used to be mostly NASA and a major aerospace company, Lockheed Martin, Lockheed, also Grumman, Boeing, but now you have so many companies. LA is really a brass place. There's so many aerospace coming in. We're just talking about the Space Force. They have Small Business Aerospace Day. They have Vast Space, SpaceX, and the Kitai, the Japanese American robotic company. They just expanded facility in Torrance. Then another company called the Astroscale. They actually bought 35,000 square feet in Torrance. And there are more coming companies. There's a company, aviation, where about called Varda Space and the Impulse Space. And I know there are people keep coming in, and the small business also growing. And the way that Alabama continues to connect with people here from major aerospace industry, small industry, different companies, educator, professor, teachers, students. We have students here encouraging, and the professional. That's the way how Alabama continue to help everybody to continue to build a family together. So today we have our leader, our distinguished speaker from our family, Dr. Jeff Puschell. He's very well known. You probably know him already. So he will also tell you a little more about himself. A very exciting story. You can see one of the charts. But main thing is this year he was inducted to the National Academy of Engineering 2024. So it's a very yeah. Thank you. Yeah. Uh, yes, yes. Yeah, it's fine. Don't worry. It's okay. He feel, but it's no problem now. Don't worry. And so basically, he's big news for him, also for the community, for LWA, and his LWA fellow. He is also our Region 6 Director for Education. You should look at his education conference, Region 6 Education Conference, and Dr. Menamet has been speaker and helping for the conference as well. If you're interested, please contact us. By the way, as you know, they also include high school students. So, Monica, please help it. And Fumi, you can join. You can submit a paper now. Dr. Michelle conference. They include high school students. So it's advertised. So that's how LA continue to do. And of course, these days, after pandemic, things are a little bit different. Some people stay online, so we're trying to get people out as much as possible. We're still in the process. So please stay in touch with us. If any question, please let us know. So without further ado, let's welcome Dr. Jeff Puschell.
Well, thank you so much, Ken. I appreciate that introduction, and I'm delighted and honored. Thank you for coming. I'm probably going to go through this at a fairly leisurely pace. I don't want to keep anybody out beyond the time, but one of the reasons we decided to have this talk was there was interest based on a previous talk that I gave of being able to go in more. So I will do that in this talk, and I'll be around for questions, hopefully answers afterwards. Ken, that prompts a question to you. When do we have to be out of this room? 9 o'clock. Okay. Yeah, I thought it might be 10 o'clock is what I remember from our past visit. Okay. By the way, Yamamoto Sama was still pitching in the bottom of the fifth, so I thought that was really good news for the Dodgers. So, well, so tonight I'm going to talk about hyperspectral coastal water imaging in space. This is something that I've worked on off and on, but spent a remarkable amount of my time working on for the past 40 years. A little bit more than 40 years, actually. This frame you see here at the beginning is based on MODIS data. MODIS is an instrument that I'll talk about today, built by Raytheon. Actually, it started when it was fused at Santa Barbara Research Center and was launched after that company became Raytheon. And what you see here is a sequence of frames showing how biological productivity changes in the ocean. So you can see South America to the west, of course, is the Pacific, with the Galapagos Islands that you can just barely make out there. And of course, to the east is the Atlantic with the Amazon Delta. We have a pointer, Ken, we have a pointer, Ken. Well, don't worry about it. I can just. Okay, I don't want to damage the screen, but or anybody in the audience that it gets out of control. Yeah, that's right. That's right. Yeah, if that happens, yeah. No, I'm not known for that. Oh, they can't hear me. Okay, well maybe I should hold it. One side. Okay, I'll hold the microphone. And then if I need a pointer, I'll just pick that up. Okay, if you go back to the. All right, thank you, Ken. And so you can see how things change. This is basically showing variations in biological productivity. So the green that you see on this slide, represents vegetation. Instruments like this are very sensitive to chlorophyll, essentially, and I'll explain how during this talk. And you can see it changes over time. So what we're interested in doing with hyperspectral coastal water imaging is looking at this in much more detail spatially, temporally, and spectrally. All right, Ken, please go to the next slide. Okay, well, let me introduce myself to you. I'm so happy to see so many friends and former colleagues in the audience today. And many of you know me, but let me just give you the quick story here. So I worked for Raytheon for more than 25 years, but about a year ago, a bit more than a year ago, I retired from Raytheon and started at Northrop Grumman 2 weeks later. And I've taken a lot of abuse for that, verbal abuse, not because of going to Northrop Grumman, but because I didn't really retire. I had no break in between, really. I was even teaching a class at Cal Poly San Luis Obispo at the same time, and so really there was literally no break. But that's okay. I enjoy working in this field. It's a lot of fun. But there is more to life, so things may change here in the not too distant future, but it's been good. So I have more than 40 years basically doing what I do, which is designing instruments that look at the Earth from space. My PhD is in astrophysics, and I happen to think, not surprisingly, that scientists, people with a science background, make very good system engineers. And the reason is we understand the end-to-end problem. We understand, that we're trying to measure something. We look at ways of doing that. We design at least the architecture for doing that. And then we follow that through all the way through the process to the end result operational system. I've written many papers, been involved in writing a couple of books as well. As Ken mentioned, I just became a member of the National Academy of Engineering. So now I really can prove that I'm an engineer, even though I certainly have fond memories of my days as an astrophysicist. And as one of my professors at the University of Chicago said, you'll always be one of us. You may think you're an engineer, but you're always an astrophysicist. Sort of like maybe being in the Marine Corps, I don't know. But anyway, I'm certainly very happy and proud of everything I've been involved with over the years. Now, many of you know my wife, Dana, as well. And she wasn't able to join us this evening, but we live in two different places. Hermosa, where I spend, 80% of my time, if not more, and in Solvang. And that's where Dana typically is. So I'm a member of the LA section, a proud member of the LA section. I've been chair of the LA section at least 3 times, maybe 4 times, depending on how many times you count. Dana's a member of the Central Coast section, though, which is really headquartered at Vandenberg Space Force Base near Lompoc. Next slide, please, Kim. Well, these are the topics I'm going to go over this evening: the importance of coastal water imaging, why we need hyperspectral coastal water imaging from geostationary Earth orbit, the history, and this will be sort of an annotated history as I go through all these different systems and try to explain their significance and also my personal connection with most of them. And then finally, we're going to look at the future, what's coming in the near future, what has just emerged actually this year. Next chart, please, Kevin. Okay, well, what is this all about, really? We're really talking about understanding and protecting our marine ecosystems, monitoring what's going on, being able to forecast what's going on. As you'll see on the next slide, most of us in the world live near the ocean, and certainly near inland waters like the Great Lakes. Huge impact on the economy. Everything is measured and modeled these days, in case you haven't noticed. In fact, I don't know how many of you have this app that I have. It's called Firewatch or something like that. I pay $59 a year to get the full up version. And I'm always being pinged, there's a fire here, fire there. Now maybe I should cut back a little bit, not have as many counties as I have. But that's coming for coastal waters as well. Harmful algal blooms developing in the ocean actually threaten tourism, drinking water supplies, and other things. There's a great interest in the Department of Defense for being able to monitor coastal waters worldwide, actually, and certainly to understand the science that goes with that for various, as you would imagine, military operations. Next chart, please. So 40% of the world's population lives within 100 kilometers of a coastline. And I would say, if you looked at the United States, it would be a higher percentage than that. The ocean economy, just in the US alone, contributes essentially 300 billion. These numbers are a little bit out of date, and almost 3 million jobs. And each harmful algal bloom averages about $50 million in impact. This slide came from Jeremy Werdell at Goddard. He's the chief scientist for PACE, which is a hyperspectral ocean color imager in low Earth orbit. And I'm going to talk about PACE later in this presentation. I may take this mask off. I have not tested positive since last weekend, and I've never really had strong symptoms. Would anybody object to that? I don't want to make you feel like I think you're okay. I'm okay. I feel fine actually. So I shall reveal my face. Um, I won't say any more than that. Okay, next slide, please. Well, this is a world map of chlorophyll distribution. And so this was basically put together by NASA from MODIS and CWIF's data. And I'll talk about those instruments in more detail in a few minutes. So the green represents areas where there's high concentration of chlorophyll A. And if you look at this map, you can see that chlorophyll tends to be in the highest concentration near continents, near coastlines, where there are nutrients that flow out of rivers and other coastal water into the ocean. There's upwelling, especially in places like California. And all of that really helps to promote this biological activity. But if you also look, you can see there are other areas, especially near the poles, where there's a lot of biological activity as well. Like the North Atlantic, for instance, one of the great fisheries of the world, pretty much everything between Quebec, Nova Scotia, and the British Isles is an area of high biological productivity. But there are other areas, typically in the middle of the ocean, where there's really no biological activity. The Sargasso Sea in the middle of the Atlantic is really quite literally a biological desert. There are no nutrients, there's no upwelling to bring up nutrients from the bottom. And so you have relatively little activity going on there. You also happen to have fairly clear water most of the time, but very little biological activity. I should mention even the South Pole is a very good area for fishing. The waters there tend to be very turbulent. It's not for the faint of heart, but it's also very good for fishing. Next chart, please. Well, today we have multispectral imagers, primarily in low Earth orbit, that cover the entire Earth every day. And MODIS, VIIRS, and VIIRS are examples of that. This is a frame taken by MODIS of California. So if you look carefully, oh, that's much better. Thank you, Monica. Thank you. Yes. Yes. Very well organized. Yeah, thank you. Okay, this is good. This is really going to be helpful. So if you look carefully, I'll have to turn it so that the finger is pointing at the right place here rather than at the audience. Thank you. Okay, so here we are. This is LA. You can see Palos Verdes, Santa Monica Bay, of course, and then up the coast, towards Santa Barbara and Solvang being there, down to San Diego. So beautiful imagery. You have a little Catalina eddy going there. But this is something you get once a day. And honestly, it's just not often enough to really understand what's going on in the ocean and especially in coastal water where things are much more dynamic. And of course, we all know, especially those of you who live along the coast know that it's been rather cloudy for the past, week or two. And you can't really count on getting a beautiful clear shot like this. And so being able to monitor this more frequently has great benefit as well. Next chart, please, Kim. Well, another area of great concern, as I mentioned already, are inland waters like the Great Lakes. So this is Lake Erie. And look at what's going on there with a lot of biological activity in Lake Erie. Lake Erie is relatively shallow, I think, compared to the other Great Lakes. Some of the other Great Lakes, I think Lake Ontario may be a bit shallower, actually. But it has major cities. Toledo is over there at the far left. I can't quite reach even with Monica's pointer. And Toledo gets all of its water out of Lake Erie and is subject to these harmful algal blooms in Lake Erie that prevent drinking the water out of the lake. Cleveland's about here. By the way, they beat the Yankees, in case you're wondering. And then the city of Detroit is also to the far left. Now, I'm going to tell you a bit about a project called Glimmer that I was involved with when I worked at Raytheon, and Glimmer's still being built over there. And early on in Glimmer, I said to the scientists, because I'm not an ocean color scientist, I really am an engineer. Although one of the reasons I love doing what I do is by freeing myself from the academy, I've been able to work on academia, maybe I should say. I've been able to work on essentially anything I've wanted to work on, including ocean color, including laser communication, including all sorts of things I never would have worked on as an astrophysicist. But anyway, I said to the science team, I said, you know, a lot of taxpayers live around the Great Lakes. Maybe you should add that to your science traceability matrix, looking at the Great Lakes. And it took a little bit of a push there, but finally they saw the wisdom of that, and they have some folks on the science team that specialize in the Great Lakes. Next slide, please. Okay, so what are we after here, really, especially at the beginning of this talk? We're after improving our understanding of these coastal water ecosystems because they're not very well understood at the moment. And I would be a bit remiss if I didn't point out that there are other ways of probing the ocean and probing coastal waters for, I think, decades. I'm not really sure when this started, but it's been decades. There are autonomous robots, actually, that probe the ocean. They sail around. They're very clever, actually. They use mechanical energy from going down and then up in the water to recharge their batteries and keep going. And I'm not sure how many of them are operating today, but quite a few all over the world. That is terrific, but we need global coverage and with more regular updates than even these in situ systems can provide. So we need to develop a global understanding of these coastal water ecosystems. And what is it that we really need in terms of the type of observations? Well, we need higher spatial resolution than we get today. So the frames that I just showed you from MODIS are basically 1 kilometer images, which is better than we've had, you know, before, but we need to do even better than that. And if you talk to the real diehard coastal water scientists, they would say they want even better than that, probably more like 30-meter resolution. But they have to keep in mind, and they certainly understand that there are other things involved as well. So that's certainly a very high and good spatial resolution to aim for. But we need hourly updates as well. And the different ways to get that. Of course, we're talking about a geostationary approach to this, where we get this kind of coverage routinely over large parts of the world. The other thing we need, though, one of the other things we need is higher spectral resolution. So the multispectral bands that we use today typically have, it depends on the system, but spectral resolution that is basically more like 50 to 100 nanometers versus 5 nanometers. Why is that important? I'll show you why in just a moment. Finally, we need high signal to noise ratio. And some of the other systems, some of the systems flying today, some of the ones that people are looking at for the future, well, I think they will prove to be valuable, cannot achieve this high signal to noise ratio. And I'll explain why that's needed as well in just a few minutes. Well, what are the long-term benefits? Well, you know, without going through all the words, to me, the long-term benefit is the ability to forecast changes in the ocean in response to other changes, weather, natural disasters, artificially caused disasters. All of these things need to be understood so we can understand what's going to happen. It's sort of like weather forecasting, where once you understand the initial conditions, you can then forecast the impact of change. So what is the answer? Hyperspectral, high sensitivity, hyperspectral imager and geo, operating in conjunction with other resources like weather satellites and air quality measurement systems. Next slide, please. Okay, well, this slide essentially shows what water looks like spectrally. So this is in the, basically the blue through near infrared. So 400 to 1000 nanometers. So our eye is most sensitive to light at around 500 nanometers or so. So in the blue-green part of the spectrum. So that's what we have on the x-axis. On the y-axis, we have the percent reflected. So, you know, you've got the sun shining, and at its peak, the peak of this curve, 12% of the light at that wavelength, which is about 720 nanometers, is reflected back toward some kind of high altitude sensor. Could be in space, could be an aircraft, could be on a balloon even. Well, you can see there's a lot of variation. I mean, down here are curves for water as well. So we go from basically 0 up to 12%. And that percent reflectance depends on what is in the water. And so pure water with nothing, you know, going on biologically has a very low reflectance. You can see it's almost 0. And depending on the wavelength, it can be, you know, certainly less than 2%, much less than 2%. Whereas some water that has a lot of biological activity has a very high reflectance. Now, this feature that you see, if any of you are familiar with land imaging, you will recognize that as the red edge. Now, I bet you didn't realize you can see the red edge in water as well. And it's for the same reason. Chlorophyll absorbs in the blue-green, where the spectrum of the sun is at its peak, but it has to, just because of the physics of the molecules that are doing this absorption, it reflects light in the red. And so if you want to find vegetation from space, the best way to do it is to look for this red edge. It's very bright and will tell you that there's vegetation there. Well, anyway, you can see there's a huge amount of variation. And so in this kind of water, very intense biological activity. In this kind of water, almost nothing is going on biologically. I should mention there are other things that are dissolved in the water. Organic dyes. There's I think it's a Danish word, I'm not sure. Gelbstoff. It sounds a little bit German, but it's actually Danish. Yellow stuff, which is a dye that's dissolved in the water. The dye forms in rivers and is transported into the ocean, coastal water by those rivers. Next slide, please. That's okay. I don't mind. Maybe I could just step, well, I'll be out of your camera. I could step over here a little bit. Okay. I mean, I don't mind just stepping forward here. That's better for me. Okay. Well, this is a rather complicated chart, but it explains a lot about why we need to do what we need to do for characterizing coastal water. And so what this chart shows is optical pathways. So this is the sun in the upper left. The sun, of course, shines down, illuminates the atmosphere, illuminates the water. IFOV is a technical term that we use for imagers. It means instantaneous field of view. And it basically defines what a single detector would see from this sensor that's toward the right. So light comes in, it scatters off of the atmosphere, off of aerosols in the atmosphere, small particles, and also molecules in the atmosphere. I can also scatter more than once. You can have multiple scattering. And you're seeing this here in the, well, this is actually, the K-path is even more complicated, where you've got light that's reflecting off the ocean and scattered. And you can think of every possible combination. I'm not going to go through them all. The real point of this chart is it's complicated. You have all these different pathways. What you're really trying to do is isolate the component from the ocean, from the water, the so-called upwelling radiance from the ocean. Well, unfortunately, it turns out when you look at the Earth from space, nearly all of the light you see is from the atmosphere. And you want to be able to isolate that, isolate the upwelling radiance from the water. Different ways of doing that. Historically,
what's been done is you try to estimate, from the measurements that you have, what the atmospheric component is, and then you just subtract it off. Well, it turns out that's not really the optimum way of doing it. What you really want to do is a retrieval, and I'm not going to get into the mathematics of how you would do that, but if you process the data using, I'm going to throw some big words out here, singular value decompositions, you can retrieve everything at once. That's really what it comes down to. Retrieve both the light from the atmosphere and from the water simultaneously. And that's better because you're not adding error. So when you just brute force subtract out an estimate of the atmosphere, you're actually adding uncertainty to the light estimate from the ocean. And so that's how you would do that. But what it also means, though, is you have to measure bands that really don't even have light in them from the ocean, but they characterize the atmosphere. Next chart, please. Well, this is why I argue that the future of space-based remote sensing is hyperspectral imaging. And the reason is very simple. We live in a complex world. We're looking at a complex Earth system. We need as much information as we can get to understand that complex system. There are different things you can do with hyperspectral imaging. One thing you can do, and we're not really going to go into this today, but certainly one of my favorite applications of hyperspectral or even ultraspectral imaging is basically imaging molecular features. So looking at carbon dioxide, water vapor in the atmosphere. And if you look at high spectral resolution at these molecular features, you can actually map out the three-dimensional structure of the atmosphere in temperature and water vapor. Very valuable for weather forecasting. Of more interest really for this talk is looking, not really imaging molecular features, but imaging the kind of features you saw on the previous chart. Broader band features that basically tell you what things are made out of. So with multispectral imaging, you can certainly distinguish rocks from trees and water. And even in some cases, you can tell, perhaps what kind of a tree it is, or whether it's a tree versus corn or whatever. With hyperspectral, you can identify the exact species of say, phytoplankton in the ocean. And you'll see an example of that later when I show you some of the early PACE data. The real problem with hyperspectral is dealing with all the data. And I could probably give an entire talk on that. Basically, what it comes down to is it's very difficult to transmit all of the data collected in a single orbit from any of these hyperspectral systems flying today, which means even though you're covering the Earth every day, say from a low Earth orbiting satellite, you're only able to send down maybe 10 to 20% of the data that you do collect. Well, if you don't believe me, believe that the future is hyperspectral, let me tell you the future is now. There's a GEO environmental satellite program, formerly known as GOES, now known as GeoXO. They've just awarded all of the next generation systems, and 3 of the 5 are hyperspectral. So the future is coming very soon. In the early 2030s is really what we're looking at for this. Yes, Ricky. Yes, Ken, could you? Oh, yes, absolutely. Yeah, this. Yeah, oh, yeah. Oh, yeah. Well, I showed you the previous chart showing how the reflectance varies according to what's in the water. So that is, going to look at all these different pathways. So A is the one, that tries to capture that. So the sun is shining, illuminating this eye fog, and out of the water comes this upwelling radiance that is reflected light, reflected sunlight. Well, yes, but that's really what they're measuring. Yeah, yes. But when you said refraction, now you made me think of something else as well. So because there is refraction, you have Fresnel refraction for light coming out of the ocean. And that depends, the exact amount of refraction depends on sea surface roughness in addition to what's in the water. And so over the years, I've done a lot of detailed modeling of, this process basically. And one of the input parameters to that is wind speed. And the reason that's an input is it tells you what the surface roughness is going to be. And if you're familiar with some of the techniques that are used in radar, for example, you can measure wind speed using on the ocean surface wind speed by looking at the radar return. And what you're really doing there is you're correlating the radar cross section with wind speed. So there are all sorts of indirect ways of doing these things that you wouldn't expect necessarily. Okay, let's go back, Ken. And by the way, feel free to interrupt me. Normally, it may be better to wait till the end, but I think in this case, I want to have a more interactive, dialogue. Yes, no. What a good question. I love your question. No, I didn't ask him to ask me that. Okay. Oh, yes. I'm sorry. Ken has asked me to repeat the question. So the question is, how much of this processing that I talked about can be done on board? And I will say it depends on who you ask. If you ask me, I would say almost all of it can be done on board. And I think eventually it will be done on board. The problem with doing it on board, and it's a legitimate concern, I don't mean to make light of it in any way, is the scientists, of course, want all the raw data on the ground. And certainly early on, that's appropriate because the reality is, there's limited understanding of what's really going on. So you want to get all the data, the rawest data you can get. You want to archive it. I mean, what they do today is they, over time, over decades, they improve the algorithms. And they go back when they come up with, a better approach. They go back and reanalyze all the data they collected in the 1990s or whatever using the new algorithm. So there are legitimate arguments on both sides. But I think you can, once you understand, what I'll call the nature of the science, you can do this processing on board. And ideally, what you'd like to do also, because in some cases there are immediate needs for this information, you want to be able to broadcast, the data products directly to users on the surface of the earth. So I think there's a growing realization that it's worth the trade to get more of the data. But I think there'll always be a need or certainly an interest to send, raw data, at certain times, just to make sure that, our understanding continues to improve. So, thanks again for that question. Yes. There are no silly questions. Okay. Yes. Yeah, thank you. Thank you for that question. I have to say I took out a lot of charts. That was one I took out with the intent of explaining that. So thank you for asking me to do that. So let me just start at the beginning. Okay. Panchromatic imagery is where you have a very broad spectral band. And the idea there is to collect as much light as possible so you can go to a better spatial resolution or even look at visible wavelength light at night. And the VIIRS day-night band is an example of the latter application where it has high sensitivity and you can literally see reflected moonlight at night from the surface of the earth. Multispectral will typically have on the order of 10 spectral bands. So 10 to 30 spectral bands with roughly like 100 nanometer resolution. The bands are not contiguous, they're spread out over the spectrum, and they're really intended to focus on specific applications. So for example, I talked about the red edge. There's a metric known as NDVI, which is a vegetation index, basically, that combines two different spectral bands, one on the red edge and one off of the red edge, but they're not right next to each other. Excuse me. The next one is hyperspectral. So hyperspectral is a higher spectral resolution. So typically 10 nanometers. So we've got multispectral, that's 100. Hyperspectral is typically 10 nanometers, so it's higher spectral resolution than the others. But the other characteristic it has, it is the spectrum is contiguous. So all the individual wavelengths are right next to each other. And so you get a complete spectrum. And by having that kind of continuous information, you know, if we were to go back to, you know, the slide that shows the reflectance versus wavelength, you can see that you would have complete description of those spectral features. And that gives you the information you need to look for very specific things. So part of what happens when you analyze hyperspectral data is you expect to find certain things in that data. Chlorophyll A, for example, it has a spectral signature, and you look for that signature and you find that it's there in a certain concentration. As you go through all the possibilities that you know of, you may find that there's something there that you don't know. And that's when it gets really interesting, right? It's like, ooh, there's something here that we don't know what that is. So, and so that gets everybody very excited. I will mention there's another level of spectral resolution called ultraspectral. Now, I'm sorry to say, and people tend to confuse hyperspectral and ultraspectral. And I'm sorry, it's deliberate, actually. They don't want to scare the customers, the government customers, by calling it ultraspectral. But it's yet another factor of 10 or more better in spectral resolution. And that's the resolution that you use to image the molecular features in the atmosphere. So you really need high spectral resolution for that. You can also use that to find trace gases in the atmosphere and all sorts of things. Now, some of you know my daughter, oldest daughter, Anne, who married a German guy who got a master's degree in atmospheric science at the Bremen University in Germany. He's a German guy. His dissertation was on using a European ultraspectral instrument to look for evidence of weapons of mass destruction. Now, I think in the United States, that would have been a little bit, it would have been difficult to publish that dissertation for one thing. But in Germany, you know, it's like, okay, it goes, yeah. So, but anyway, there are all sorts of applications for this kind of spectral data. Yeah, thanks for your question. Okay, keep going, Ken. Okay, well, so this slide illustrates the concept of hyperspectral imagery. You have a camera, hyperspectral camera. These hyperspectral cameras produce what we call data cubes. And the reason we call them data cubes, I think, is illustrated pretty clearly here. So in sort of a normal image, you have a two-dimensional distribution of pixels. And in a hyperspectral image, you have a cube, right? You have a third dimension, that's the wavelength direction. And again, this is a contiguous spectrum. And so just like this is a contiguous two-dimensional image, this is really a contiguous three-dimensional data cube. Next chart, please. Well, the intent of this slide is to really try to illustrate what we're trying to achieve here with hyperspectral. We want to be able to separate all these different components, all these different places that create the signal we see, whether it's the bottom of the ocean, whether it's scattering in the water, whether it's reflection off of the sea surface, or the scattering off of the atmosphere itself. And with hyperspectral, we can separate all these different elements out. Not only can we just see that it's in water scattering, we can see what is actually doing the scattering. Next chart, please. Okay, well, now I'm going to go through the history of coastal water, ocean color imagery, starting with the coastal zone color scanner from the late 70s, and continuing to where we are today with the PACE ocean color imager in sun synchronous orbit, and Glimmer, which is still being developed at Raytheon, almost within walking distance of where we are right now. Next chart, please. Okay, well, CZCS was the very first space-based coastal water imager. And back in the 80s, I was doing work for the government, uh, uh, different applications related to the ocean. As I mentioned to some of you, before the talk, we would go out and measure the in situ properties of the ocean if we could. But we weren't necessarily interested in just knowing what was going on, say, in the Channel Islands or in Hawaii. We wanted to know what might happen in the Mediterranean or other parts of the world of interest to the Department of Defense. And so we needed to be able to at least get some idea of what the optical properties of those other coastal waters was like. And the only way we could do that back then was with CZCS. It was a pretty primitive instrument by today's standards. It did have 6 spectral bands. One of those was a thermal band, which really didn't work very well. It was really the first attempt to have what I'll call an all ocean type of imager, where you would measure biological characteristics of the ocean and its temperature. But as I said, the temperature really didn't work. But it was all we had until CWIFs came along in the late 90s. So we went for more than 10 years, really, without having any remote sensing of the ocean from space. Next chart, please. Well, that brings us to CWIFs. So CWIFs was built up in Santa Barbara by Santa Barbara Research Center, which is where I basically started my career at Raytheon. Actually, the day I walked in the door, it was still Hughes in Santa Barbara, but it became Raytheon shortly after that. CWIFs was the very first commercial ocean color imager. The customer was Orbital Sciences Corporation, which is now part of Northrop Grumman, but the part of Orbital that was really the customer became Orb Image, which would throw all sorts of series of corporate dislocations, and that legacy business is now part of Maxar, which operates Worldview and Legion, and probably the leading commercial imaging and remote sensing company in the world right now. So CWIFs was operated until 2010. The instrument itself actually did extremely well. It never really showed any degradation, but an incorrect command was sent to the spacecraft in 2010, and that was it. And I never heard from it again. 8 spectral bands, I'll show you what those are in just a moment. About 1 kilometer resolution in the highest resolution mode. Swath width, only about 1,500 kilometers in high resolution and 2,800 kilometers in the lower resolution. Now, we talked about some of the limitations of hyperspectral data today. Well, back then, multispectral data had a data rate limit on it as well, so they couldn't actually send all of it. And so that's why they had 2 different swath widths. And so higher resolution got a narrower swath because of the data rate limitation. Pretty small imager compared to most of the things that I've worked on. This is a rotating telescope. So here you see the aperture. Inside that assembly is a telescope that rotates. That rotating telescope approach was used in VIIRS, which I'll be telling you about in just a few minutes. I never worked on CWIFs itself. I did get involved with CWIFs because CWIFs was launched actually just before I joined Santa Barbara. But it turned out there was a spare flight model of CWIFs. And so I worked with that to see if we could find an opportunity to fly it. And we did not succeed in finding an opportunity, but I was able to help Raytheon donate that spare flight unit to the Smithsonian. And so it's going to be part of a new exhibit at the Air and Space Museum as soon as they finish it. I was just there a few weeks ago, part of my trip to DC for the National Academy induction, and they're still working on the air science part of it. So I'm looking forward to seeing that new exhibit with the CWIF spare scanner that the Raytheon donated to the Smithsonian. Next chart, please. These are the 8 spectral bands and CWIFs. I'm not going to go through them, but these are what I'll call the 8 canonical ocean color bands. And they're found really in every ocean color imager that has flown since SeaWift. Now, some of them have slightly different bands, but these are the 8 bands of most interest. One thing I should mention that was on the previous slide is many people think that SeaWift's provided the best ocean color data ever collected. And the reason is it was optimized for ocean color. And so it had a polarization scrambler, for example, to essentially eliminate the effects of polarized light on the data. Ken, could you go back to the previous slide for just a moment? It also had a mechanism that tilted the entire imager to avoid glint. You don't want to be looking at glint. You want to be looking at the upwelling radiance from the ocean. Go ahead, Ken, to the next slide. Actually, go beyond to the one after that. So MODIS is the next one in this sequence. So MODIS has 36 spectral bands. Now, I've had people ask me, well, MODIS must have been hyperspectral, right, with that number of bands. And no, it wasn't, because those bands are not contiguous. So I would say probably the most ambitious multispectral imager ever built. Still operating today. One was launched on Hera, built by Lockheed Martin in 1999. The other one built by Northrop Grumman Space Park, launched in 2002. Both of these are coming to the end of their lifetime. They've both done extremely well, but they're both drifting now in their orbit. And so they're not really sun synchronous anymore, but they're still delivering useful data. So 36 bands, roughly a third of those bands are dedicated to ocean color. You can see this frame from the Gulf of Mexico, extreme biological activity going on there around the Mississippi Delta. Again, you're only getting that kind of data once a day. Next chart, please. Well, the real value of MODIS for the rest of the field is how MODIS pioneered calibration techniques, and especially for the reflective part of the spectrum. So I don't really want to take the time to go into detail, but if you have interest in that, see me after the talk. I'll be happy to tell you all about that. I did work on MODIS, actually. I didn't work on SeaWift's, but somewhat to my amusement, I was the sort of the last program manager for MODIS every year. So not exactly a role that I'm used to having, but next slide. Okay, well, the next step is VIIRS. So VIIRS followed MODIS. This is an operational system. MODIS was an earth science system, 22 spectral bands, because once the science was better understood from MODIS, they didn't need as many spectral bands, really, for VIIRS. Although some people are unhappy with not having as many bands. And there's a more complex answer than that, too, that goes with that. But basically, if you go to the next chart, Ken, you can see how MODIS, how MODIS certainly contributed to VIIRS, but VIIRS combined the best features of all these different systems. So the rotating telescope from SeaWift's, the calibration systems proven in MODIS, the radiometric accuracy and sea surface temperature band continuity from AVHRR, and finally, the high dynamic range imagery from OLS, the operational line scanner, very clever, ahead of its time system that was flown in DMSP, the Defense Meteorological Satellite Program. Really an amazing system for its time, especially. All these things went in the VIIRS, which made it complicated to really build the first VIIRS. I was one of the chief engineers for VIIRS, especially during the dark days. I was asked to come in and help VIIRS, and also was the chief scientist on VIIRS for quite a while. Next chart, please. Okay, well, now we're going to move to a European system, MERIS. And one of the reasons I bring up this system, aside from completeness, is that it really forms a bridge between multispectral and hyperspectral. So MERIS, as you can see here, consists of 5 different cameras. It uses a different architecture. So everything we've talked about up to this point is what we call a whisk broom scanner, where you have a mirror, typically, sometimes 2 mirrors, that's moving relatively rapidly, covering a wide swath on the Earth. In the case of Maris, we have a push broom imager. And so you have these cameras that are fixed, that are pointing at the Earth as the satellite orbits the Earth, and the satellite itself is doing the scanning. Well, it turns out these 5 cameras are all hyperspectral, but they never used Maris for hyperspectral. They always created these virtual spectral bands and sent those to the ground. Now, I had nothing to do with Maris, except for asking some questions at conferences about, are you sure you never use the hyperspectral data? And why didn't you do a better job with the calibration? Because if you look at Maris data, you can see 5 distinct imager stripes or swaths. And they swear they never actually looked at the hyperspectral data, even for engineering purposes. Well, Maris flew on something called NVSat, and that was another one where the spacecraft failed in 2012. A better version of Maris is flying today, something called OLCI. That was launched more than 6 years ago, and is doing well. It has more spectral bands, better spatial resolution, really a very effective system. Next chart, please. Okay, well, everybody is interested in small satellites these days, including me. And there have been some small satellites that do ocean color imaging, and can certainly contribute to coastal water imaging. How are we doing on time, Ken? Are we okay? Yeah, okay, good. Something called Seahawk basically established the feasibility of making these measurements with CubeSats. So the Seahawk imager is a 1U CubeSat piece. It's actually a 3U CubeSat altogether, but one of the 3 pieces is basically the imager. It was funded by the Gordon and Betty Moore Foundation just before Gordon passed away. They couldn't get money from NASA to do this, and so fortunately, the Moore Foundation stepped up and funded this. So it's in a polar sun synchronous orbit, a bit lower than CWIFS. CWIFS flew in a 705 kilometer altitude orbit. This is a bit lower. The PI is a guy from the University of North Carolina, Wilmington, John M. Morrison. Cloudland Images in Santa Barbara actually built this imager. The guy who runs Cloudland Instruments was the chief engineer on CWIFS. His name is Alan Holmes. And I think he does most of his business selling cameras for astrophotography. But they built this instrument along with a few other, and there were some other people that I know up in Santa Barbara that participated in this. This is also a push broom imager. Now, the advantage of a push broom imager over, say, a whisk broom imager is better sensitivity. But the disadvantage is a narrower swath. And so, you know, the Seahawk people are very proud of what they've accomplished in terms of resolution and signal to noise ratio compared with CWIFS, but they don't have anywhere close to global coverage because of the narrow swath. Of course, with small satellites, you can make up for that by having a lot of them and covering the Earth. Well, NASA finally got on board with this after it had already been launched. And Gene Feldman at Goddard was intimately involved in this. And through a Space Act agreement, NASA got involved, helped with the calibration and validation, and also archiving the data, et cetera. So you see some data. This is from Hawkeye, as they call it, and this is from MODIS. So it's really hard to tell anything, frankly, at this level of resolution, but you can see that it kind of looks the same. If you look closely here, you can see how Hawkeye mapped out chlorophyll A in Monterey Bay up in Central California. Next chart, please. Well, I took this chart off of one of the NASA websites. It's a little bit unfair, frankly, but it's still interesting to see the progression. So at the right, we have NVSat, the one that Maris flew on. At the far left, we have the 3U satellite Seahawk with the Hawkeye imager. Clearly a big difference, 8,000 kilograms versus 4 kilograms. But of course, NVSat has a lot more on board than just a narrow swath. imager. And the same is true for the other systems shown here. But it really does reflect the trend that we're seeing. Again, here you see the C-STAR satellite, which was dedicated to CWIFs. There was nothing else on board that satellite. And of course, this was based on basically 1980s technology. It sat on the ground for a long time after it was finished. And so if we were to build C-STAR today, it would be much smaller and much lighter. So we're kind of comparing trends in technology here as well. But this does reflect a trend. People are moving away from these so-called Battlestar Galactica satellites in favor of more mission-focused satellites. We're going to see that everywhere, certainly in the DoD world and in the civilian world as well. Next chart, please. Okay, well, let's move on and talk about GOSI. We're now going to geostationary orbit. GOSI really is the first geostationary imager dedicated to coastal water imagery. Built by, it actually is a South Korean system, but it was built by the French, by Airbus. And GOSI itself was launched in 2011. GOSI 2 went up in 2020. GOSI 1 basically just stared at an area near the Korean Peninsula with 8 spectral bands, which should look very familiar to you because you saw them on the CWIFS chart. GOSI 2 has 12 spectral bands, better spatial resolution, so now we're down to 250 meters, but they're all multispectral bands. But it does cover the full disk as well. So in many ways, GOSI 2 has really taken most of the steps really needed to get the information that's needed to improve our understanding of coastal waters. The one thing it's missing really is the contiguous spectral coverage and the high spectral resolution. Next chart, please. All right, well, let's really get into the hyperspectral world here. So the PACE Ocean Color Imager was launched in February of this year. I think it was February 8th. I think it may be on this chart somewhere, but anyway, it was in February. I was on the PACE science definition team. I was the only engineer. I guess I could say I was the only astrophysicist too, but the only person from industry on the science definition team. And it was a real pleasure to serve on that team. Almost literally, PACE Ocean Color Imager is a hyperspectral CWIFS. It has a rotating telescope. It has about the same spatial resolution. The swath is about the same, not surprisingly. The altitude's a little bit different, but essentially the same. Spectral resolution or spectral sampling really is fairly high, 2.5 nanometers. So well past the threshold for what is considered hyperspectral. Excellent instrument calibration. PACE was really developed by NASA, by Goddard Space Flight Center, using an architecture that Chuck McLean, who has retired from Goddard probably about 10 years ago, I think, by now, developed. It is called Orca. Very clever architecture. And for those of you who are engineers in this field, I think you'll find this interesting. So what I find so clever about the Orca architecture is that it basically does what we call time-delayed integration or sample averaging, whatever you want to call it. There are different names for it. In a whisk broom scanner in the scan direction. So if you look at this chart, what you see up here is the spectrum from a single pixel. Well, normally when you're flying, say, a push broom, you fly in this direction. So you basically collect rows of pixels and you build up the spectral image over time. In this case, it's a 1 pixel scanner, and you're using this redundancy in samples to really improve the signal to noise ratio. So you're addressing the main limitation of a whisk broom, which is relatively low sensitivity, by being able to do this averaging in what I call sideways. Well, what's the penalty? This sounds too good to be true. Well, the penalty is you have a 1 pixel scanner, which means this thing really rotates fast. And all I can say is stand back when they turn this on. You don't want to be in the room with this thing going at a very high scan rate. Next chart, please. Yes. Yes. Yeah, another good question. The question is, why do you go why you go into the ultraviolet, really? Uh, and the thing is, when you go to that short of a wavelength, you're not even getting down to the surface. You really can't see the surface of the ocean at that wavelength because of the ozone absorption. And so, the intent again is to characterize the atmosphere. And so you're characterizing a part of the atmosphere that's going to be higher up in the atmosphere. And as you would know, because Jim, is in this business, it's very hard to find coatings that are going to work well from 340, all the way out to 895. Typically, you don't expect to do better than a factor of 2, and we have Zygo sitting right next to Jim. She'll tell you even more how hard that can be. But that's what they did. And, Glimmer is going to do something different, but not much different. They're going to go as far into the UV with Glimmer as they can. And no promises there because I'm sure there's better information now than there was at the beginning of the project, but it really depends on what you get, what those coatings really turn out to be. And there is a lot of interest in the ultraviolet now and other mission areas. Depends on what you're really interested in, but if you're interested in things that are in the upper atmosphere, there's a lot to be said for the ultraviolet. But I don't think they're not really planning to do that with PACE. So it is really hard. Okay, next chart, please, Kevin. Okay, well, this is very early data from OCI. So I mentioned it was launched on February 8th, and this data was collected on February 28th, which just happens to be my wife's birthday, Dana's birthday. She's a zoologist, by the way, so this would be a personal thrill for her to have this data presented publicly on her birthday. But as I was saying before, if you look at this, and this is the coast of Africa, so Cape Town's over here. This is a very interesting part of the world for many different reasons. But you can see from this PACE data, you can recognize the signatures of specific microorganisms. Of course, this is highlighting the chlorophyll A concentration. Out here, you see true color, which sort of comes as a freebie, really, with this kind of detailed spectral data. At the same time, you're seeing all of this activity. If this were a geo instrument, if this were, say, Glimmer looking at this, you could make a video showing how this changes throughout the day. Next chart, please. Well, here's another example of PACE data. So this is from a bit more than a month later, and NASA called this PACE mission's first spring bloom. Now, April 8th in this part of the world is sort of spring, I guess. You can see there's still a lot of snow on the ground. But the sun is of course, coming up higher in the sky as the Earth continues its path around the sun. And so they're getting a lot more sunlight than they were just a few weeks before that. And that's helping to spur this biological activity. This is Nova Scotia, New Brunswick. This is Cape Cod. I'm just pointing out some things. New York City is down here. And very interesting early spring activity. Next chart, please. Okay, well, let's go back and talk some more about CubeSats. So it turns out that this really is an active area of interest throughout the world. And so there's something called HyPSO-1 that was developed by students at the Norwegian University of Science and Technology. And these students basically built on, the pioneering path set by Seahawk, which you saw, HYCO, which was on the space station. That was an NRL project. Alto 1 was another European project. Alto 1 was actually Finland's first satellite. It was developed by a graduate student at the Technical University of Delft in the Netherlands, but a guy from Finland. His project was paid for by Nokia, not surprisingly. So this is a CubeSat launched in 2022 into a similar orbit as the other ones we've just talked about, 540 kilometers. It was all COTS parts. It was a push broom imager. Spectral range, wasn't as wide as some of the other systems we saw, but gee, it's a bunch of students. They probably spent $50,000 on this satellite for all I know. Pretty high spectral resolution, pretty good spatial resolution, really 100 meter pixels. Narrow swath, of course, you got to give up something somewhere. Signal to noise ratio of 200 is okay, but you really would like to have a factor of 10 more than that to really be able to unravel what's going on. But what they envision, rightly so, is a constellation of satellites like this. I'll show you some data from the satellite here in just a moment. And what they're doing with that data is training deep learning models for interpreting future data. Another group at MIT, it's actually MIT Portugal. So it's the MIT, but they have a division, I guess you could call it. It's a school in Portugal that developed the CubeSat hyperspectral imager. That was launched in March of this year, and you can find out more about it at this website. Now, if you go to that website and look at that, you'll see a photograph of the student team. And so I gave a version of this talk in San Diego at the SPIE conference. And out of the audience emerges this young woman wearing the same dress she had on in this photograph. And she works at aerospace now. And so I think she and I are going to try to get together and just talk hyperspectral, but a very good acquisition by aerospace to hire her. So I haven't seen any data from this. It's been a few months. In the case of Seahawk, I think it took at least a year before they got anything useful that they could make sense of, and that's part of the challenge with these CubeSat systems in general, is it takes a while for them to work for various reasons that we don't have to go into here. Next chart, please. So here's data from a paper that was published fairly recently on the HypeSo data. Now, what they're doing is very primitive at this point. They're taking this data and they're basically training it to recognize sea and land and clouds, very primitive stuff. We're not into specific microorganisms yet, but you got to start somewhere. And I think, given this data, frankly, really isn't that great. They're not going to be able to go that far, but they're starting in a good place and they're going to get better and they'll fly better systems in the future. And probably 10 years from now, we'll be astounded by what they're able to learn from better data. Next chart, please. Well, it's more than just universities that are developing systems like this. Hyperspectral is becoming a very important part of the commercial satellite world. So CWIFS was the first commercial remote sensing system of any type. But now there's a whole series of hyperspectral systems that are being developed. This chart talks about one of them, Tanager 1, which was developed by Planet Lab in partnership with the Carbon Mapper Association, which is a 501c3. JPL was involved, Mike Bloomberg contributed money, and many others are involved with this. Now you say, wait a minute, Jeff, isn't your talk about ocean color and also why are you talking about methane and carbon dioxide? Well, what drove this system, Tanager 1, was the desire to have a capability to monitor methane emission, detect emission, to track it over time. to find, the sources of methane and shut them down, basically, if they're not operating the way they're supposed to. But you don't need this kind of spectral range to do methane. This is a full-blown hyperspectral imager. It's going to do land imaging. It's going to do coastal water imaging and ocean color as well. Although I don't know that there's much commercial value, as much commercial value in ocean color, certainly for fisheries. But it's going to be mostly these gases plus land imaging for agriculture and plus coastal water imaging for the reasons we've already talked about. The quality of the data is going to be okay. This is what the signal to noise ratio is going to be in the methane band, so in the shortwave infrared. And I could explain why there's a range. It's just there are different ways of operating the satellite. I think once we have systems like PACE that have flown for a while and Glimmer still to come, that can basically develop the detailed understanding that we need to interpret data from satellites like this more completely and accurately. That may be just fine for signal to noise. Next chart, please. Well, here are some of the other companies that are involved. So the NRO signed agreements for study contracts about a year and a half ago with the companies you see listed here to look at how to provide commercial hyperspectral imaging. Black Sky, as far as I can tell, is not really doing anything. Maybe they are, and they're just not telling people about it. But they really are focused on multispectral, I think. This was just a study. There was no contractual obligation to provide hyperspectral data. And I think they're finding great opportunities in multispectral now. Hypersat is developing a system with 6-meter resolution, so very high resolution, very ambitious 500 spectral bands across some broad spectral range. As far as I know, that system has not been launched. Orbital Sidekick, though, is doing very well. They've already launched 2 sets of these ghost satellites, one in 23 and one in 24. I'm not sure of the spatial resolution, but it appears, based on what I've read, to be about 8.3 meters. So again, very impressive. If the signal to noise ratio is reasonably high, this data is really going to be interesting. There's a company here really started in India, but is also located in El Segundo. I think they moved down from San Francisco about a year and a half ago. They're over on Rosecrans, actually. They're still planning to launch a constellation of 24 satellites this year and next year. They've already put up a couple of technology demonstration satellites, 5-meter spatial resolution, 300 spectral bands. And this is, honestly, this is really exciting. Yet another one called Explore, with even higher spatial resolution. It's not clear whether this was really launched successfully or not. It was on one of these transporter, rideshare missions, and Orbastro isn't always that forthcoming about what goes on with their system. So I don't know what happened, and I'm not sure anybody outside their closely knit team really knows whether that succeeded or not. Other things going on, there's another group of former Finnish students that started Kuva Space. They launched their first hyperspectral microsat called Hyperfield roughly 2 months ago. And I haven't seen any data from that, but I'm sure it'll be forthcoming. What are these guys after? Well, they're after this $47 billion market for hyperspectral imaging that is expected to occur by 2032. Big bucks. All right, next chart, please. Well, finally, let's talk about Glimmer. So Glimmer is still in development. As I mentioned before, it's being built over at Raytheon on El Segundo Boulevard. It's going to go into GEO. It's going to have about 250 spectral bands, 300-meter ground sample distance at nadir. Very high sensitivity. I'll show you a chart here in a couple of minutes showing very high signal to noise ratio as a function of wavelength. Instrument polarization is going to be low. Stability is going to be high, so better than 0.5% radiometric stability. It's going to basically register these spectral samples to the Earth using something called a landmark imager. So it's going to be a separate camera, basically, that has higher spatial resolution, about 130 meter spatial resolution in nadir, that will look at these landmarks on the surface of the Earth and register those landmark observations to the hyperspectral data. The PI for Glimmer is a wonderful guy, Joe Salisbury, at the University of New Hampshire. And the co-PI or deputy PI is Antonio Menino at Goddard. And Antonio was also involved in CASE, but these two scientists really are leading a fantastic science team. Ed Chung is the program manager over at Raytheon. Jeff Yee is the chief engineer. And John Bloomer, another recovering astrophysicist, as he calls himself, is the lead system engineer. Okay, next chart, please. Well, I had something to do with getting Glimmer started, and so I knew we were going to win this proposal. I just knew it. Now, of course, I wouldn't have been embarrassed if I had been wrong. But I bought this car at BMW of Santa Barbara a couple of weeks after we sent in the proposal. I was so confident that we were going to win that I got personalized license plates. And I still have, even though I now work at Northrop Grumman. Okay, next chart. So I could probably spend 20 minutes just on this single slide. So this is really the Glimmer mission. This is what Glimmer is going to do. It's going to unravel all of what you see on this chart. So here you have a river flowing out into, say, the Gulf of Mexico. And there are different things that go on that would vary over seasons, vary in response to severe weather, like hurricanes, for example, or severe weather upriver. Of course, you have coastal currents, you have these harmful algal blooms, seeps and spills, major leaks sometimes from these offshore platforms, all sorts of biological activity going on in the ocean. Glimmer, by being able to revisit these areas hourly or even better than that, depending how it really gets used, at high spectral resolution, high spatial resolution, will follow how these things change. They'll find causes and effects and ultimately, put that understanding into prediction models for predicting what's going to happen, say, in a future event. And so really what they're going to do is quantify these biological and biogeochemical processes and use the quantification to predict future events. What I used to tell the folks at Raytheon is someday we will see Glimmer data on the Today Show or Good Morning America, whatever your favorite show is, Channel 5, where, yes, Ricky. So I would say Glimmer data in particular. Okay, let's just talk about Glimmer for the moment, and then I'll answer the other part of your question, or the real part of your question. Glimmer is not a climate sensor, right? It's very much in like real time. Something happens in a river or coastal water, and it causes a change that's observed and quantified and understood. You could argue that Glimmer will provide a baseline, for future, climate-related studies. In other words, say 30 years from now, when people are making similar observations, they'll say, that's interesting. That's exactly what we saw in Glimmer, or it's not. Probably won't be. It'll probably be similar but different. And there'll be comparisons like that. Glimmer is going to be well calibrated. But it's probably debatable whether it'll provide what people call climate quality data. And so it's not a climate sensor. Now, part of the problem with ocean color data is that not all of the systems, were calibrated. So CWIFS was pretty well calibrated. MODIS was extremely well calibrated in Beers. And so there is sort of a climate quality data record that's been created and will be referenced in the future. But, when you're coming over only once a day and not every day, has clear skies or whatever, you're not going to have, as much detail as you would like. Uh, the other thing about, coastal water, even though it's very dynamic, it's not like the atmosphere, right? It changes more on hourly timescales rather than minute timescales. But I think, if you look at, what people are talking about now, with these hurricanes that we've seen this year and in recent years, where they go from category 1 to category 5 in hours. I mean, that's something that we really haven't seen until recently. And so, people are saying that is due to, the effects of climate change. And, over time, we'll see how that changes. Maybe 20 years from now, some of us are still going to be around in 20 years, right? I mean, we'll see. We'll see, what really happens. I was happy to see, by the way, something I saw yesterday in the newspaper, that we're actually one of the best places for climate change. Do not move to Texas. I know a lot of people in California are moving to Texas. Do not move to Texas. Texas is like ground zero for climate change. So it might depend on where you are in California, but some of the inland areas are going to be affected more than other areas. And of course, we're all going to be affected by changes in precipitation, but we'll see how all that works out. But glimmer is most emphatically for transient phenomena. And again, it'll form an archive that is, referred to later on, but the intent is not to study climate change. Okay, let's go on to the next slide. Okay, so Glimmer collects data on at least 10 different areas. Now, all of these areas are programmable. I actually created this chart way back when, and my intent was not to say, okay, these are the 10 areas that we're going to measure every day. It was just sort of a day in the life kind of simulation where we said we could do 10 areas like this multiple times every day. And so you said, wait a minute, I don't see 10. Well, there are a few out here as well. This is Hawaii, South Pacific, a couple of South Pacific areas as well. So the idea would be to go from east to west. So the sun comes up on the east, you look at the Amazon Delta first, you go to the Caribbean, the East Coast, Gulf of Mexico, etc. These little sort of aqua or turquoise colored dots that you see are the landmarks that I mentioned before. So you can see that a lot of them are along coastlines, Gulf of Mexico, etc. The landmark imager will look at those at the same time that the hyperspectral data is being collected, and that information will be used later to create spectral imagery that's registered to the Earth to a very high level of accuracy and precision. Next chart, please. No, except there was sort of a political reason where people didn't want to, because they didn't think it was important enough. And it's like, you got to be kidding. Tell that to the people in Chicago or whatever. Yeah, seriously. Well, see, that was during the dark days of, it's like, Jeff, we are not looking at the Gulf of, we're not looking at Lake Superior or whatever. Yeah, right. But the thing is, you look at how big these areas are. Like, this is the Gulf of Mexico. And you can see the Great Lakes up here, and you can see there are landmarks by the Great Lakes too. You can cover all of the Great Lakes in one swath. And so they're going to do that. They've reformed their point of view on this. So finally listen to the taxpayers. Okay, let's go on to the next chart. So we're engineers, right? We need an official definition of the Gulf of Mexico. And so this is it. Azimuthal angle range of 2.65 degrees and a swath width shown here. And so you see, well, wait a minute, you're missing this, aren't you, Jeff? No, well, that's the Bay of Campeche. So that is not the Gulf of Mexico. Just want to make that clear. But we covered this. The intent was to cover it in less than an hour. And we had to slow it down a bit to achieve the high signal to noise ratio that the science team wanted. And so we're still doing it in less than 70 minutes according to our predictions, which will still be better than anything that's flown before. And so we're going to be okay. Next chart. Well, this is a chart that John Bloomer put together. It's an excellent chart. A lot of detail that unfortunately you can't read. And so I apologize for that. And these numbers I can't even read. But I know that this is a signal to noise ratio of 3,000. So you can see the peak SNR is up around 3,000. The red lines, which you can't also read, are the requirements. And so you can see the required signal to noise ratio varies with wavelength. And it's quite high everywhere. The most challenging spec to meet is in the near infrared. This is the chlorophyll fluorescence band, which is extremely important for quantifying chlorophyll. So they really want this number for signal to noise ratio, and that one number actually drives the rest of it. That's why you see such tremendous margin here. You're getting all that for free because you're trying to get this. That's what it comes down. Next chart, please. Okay, well, the next step in this process from GEO is something called OCX. And OCX is part of the operational GeoXO system. I mentioned that before. GeoXO really is the operational follow-on to Glimmer. And it was won by BAE Systems, formerly known as Ball Aerospace. And Ball's, was an excellent company. But honestly, having been involved with Glimmer and at Raytheon, I was certainly hopeful that Raytheon might win that. But it was not to be, and I won't get into any more detail than that. But Ball is going to do a tremendous job. They've been very successful lately in winning a lot of these systems, so they have a big challenge ahead of them. But if anybody can do it, Ball can do it, or BAE now. So their numbers are a little bit different than what I showed you before. This was actually an ad that they had in Space News just a few days ago. They sent it to me as a PDF file, and so I just took out parts of it, put it into this presentation. So, but the numbers are essentially the same. They make a persuasive case for the importance of OCX. So let's go on to the next slide, please, Ken. Okay, well, in closing, emerging hyperspectral ocean color and coastal water systems are going to revolutionize our ability to understand what's going on in coastal water ecosystems. By doing better in every way you can imagine: spectral resolution, spatial resolution, and temporal resolution. The wealth of data that will come from these systems will allow us to recognize, quantify, and track a large number of different constituents in these waters. We'll be able to track the response of ecosystems to environmental change, whether it's gradual or sudden, from storms, oil spills, et cetera. I think of most importance, and I think this will benefit DoD considerably, we'll be able to forecast the impact of these changes. And, over time, I think we'll be able to, make forecasts, reliable forecasts of things like this days in advance, maybe even a week or more in advance, which will be extremely helpful in planning different military operations and tourism, all sorts of things. PACE was launched February 8th, as I mentioned. Glimmer, as far as I know, is still on schedule for launch in 27. As I just said, Glimmer is a pathfinder for OCX, and I think that's scheduled to go up in 2032. But meanwhile, with all these really excellent systems being developed, we're seeing, a proliferation of small satellites, each one of which has less capability, but the combination of these systems basically cross-referenced or cross-calibrated with these much better systems are going to open up all sorts of other possibilities as well for improving temporal resolution especially. So thank you very much. This was a long talk, and so thank you for bearing with me and staying awake during this long talk.
Are there any questions? Yes. Yes. That's a good question. So the question is in reference to Europa Clipper, which was just launched on its way to Jupiter's moon, Europa, which is thought to have more water than we have on the Earth, which is pretty amazing. Right, but it's beneath ice, and so it's going to be probed in very different ways from what we talked about here. It'll be probed, with radar. Someday it may be probed, by submarines on Europa, which would be really cool, actually. I would say if you look at the broader, range of technologies used to characterize the ocean, because a lot of RF technologies, microwave, passive microwave, and active RF, with scatterometers and ocean surface wind radar. I mean, things like that are more related to what's going to Europa than what we talked about today, but there's certainly an overlap in the technology. Oh, question on what? Oh, okay. Go ahead, Christian.
I was curious what factors contribute to the noise that you see when you're transmitting.
Oh, and you're talking about noise in the data?
Um, it was when you were mentioning noise to signal ratio, like signal to noise ratio, I believe. Where was that noise coming from?
Oh, okay, that's a good question. So it comes from different sources. The dominant source of noise is basically fluctuations in the signal itself. And so even though you have a very strong signal, it's not perfectly stable, and it's governed by Poisson statistics. I don't know if that means anything to you, but it's sort of like almost like a popcorn noise, where you have these discrete events. The detector, the solid state detector, creates a photocarrier. You can sort of think of that as an electron. When a photon of light hits it, and the rate of the photon rate is not perfectly uniform. And so that's actually the dominant source of noise. Another source of noise is basically scattered light inside the instrument. And that's a much weaker source of noise, but it's something you can't neglect. Yet a third source of noise is dark current in the detector. And so even if you, say, cover the detector so that it can't see any light, you'll still have a current, a small current, that is due to spontaneous emission of electrons in the detector material. Finally, the last major source of noise is what we call readout integrated circuit noise. And so what happens in these focal planes is when you collect these carriers in each in capacitors that are associated with each detector. And when you read out those capacitors, in other words, when you remove the charge and send it to the signal processor, there's an uncertainty that goes with that. Anytime you do anything, there's an uncertainty associated with that. Now, fortunately, the readout noise is a fairly small component typically, but in a hyperspectral system, where you're looking at a very narrow slice in wavelength and therefore a relatively small signal compared to, say, a multispectral system, readout noise can start to become pretty important, actually, in some cases. Did that answer your question?
It did, thank you.
You're welcome. Yes. Yeah, that's a great question as well. So the answer is yes, actually.
it does depend on what you're trying to do. You know, it's sort of counterintuitive for some people when they first sort of get into this remote sensing field, that you have something sitting out in geo that's smaller than something that's in a low Earth orbit that, you know, is literally, you know, hundreds of times, you know, closer to the Earth than the geo. I mean, it depends on the orbit exactly, obviously, but it could be even like 1,000, you know, times closer in Leo. But the thing is, when you're moving across the Earth very fast, you know, you don't have much time to look at the Earth. And so generally the size for a low Earth orbiting system is driven by sensitivity. You make it big enough that you can get the signal to noise ratio you need in the amount of time you have. And so as you pointed out in your question, in geo, you have more time, but you still want to get that high spatial resolution. So the size is driven by the size of the optics. And so something like Glimmer, which is, you know, trying to get 300-meter spatial resolution, you know, in the, say, near infrared, say 700 nanometers in wavelength, that still has to be, you know, a certain size in order to be able to do that. And so it turns out that it's not insignificant. So you're looking at, you know, 30 centimeter aperture for that. The other thing that sometimes is required for these systems is not only a high signal to noise ratio, but a high, what I'll call image quality. There are certain things that define image quality, like the edge response. You want to make that as sharp as it needs to be to give good quality imagery, but you don't want it to be too sharp, because then you have ringing, you know, you have these artifacts that appear. So there are a lot of things that have to be traded off, but frequently the geo systems are smaller because you still need a big aperture, but other things are simpler too. Yes. Oh, yes, I'll try. So, you know, in some ways, I'm tempted to say, you know, this is a developing field, but in reality, it's something that's been used for a long time. I mean, I remember back in the 80s, we were messing around with neural networks. We were doing what we called statistical retrievals, okay, which is much harder to say than machine learning, but it's the same basic process where you're collecting statistics on physical phenomena. And then once you've trained an algorithm, or once you feel like you've found the full range of possibilities, then you can start looking for the signatures of events like that in data. And where that's being applied most effectively right now is in weather forecasting. And again, the challenge really is in training, you know, the algorithm. The algorithm itself is very straightforward usually. It just requires a lot of data and processing. So in the case of ocean color and coastal water, you know, what's going on is again very straightforward. You have a spectrum. It has, you know, certain features. You know, from different means, such as in situ testing, what's actually in the water. I mean, you can retrieve what you think is in the water from the spectrum, but it's better to have ground truth data as well. And so something like Glimmer is going to have an extensive ground truth campaign. Sea truth is actually what we used to call it. And PACE already has that going on. And so it'll be a combination of things that will allow future systems to almost just look at the spectrum and you know, by looking at certain ratios and you know, very quick processing, you know, be able to say, yeah, it's this much concentration of that microorganism, et cetera, et cetera. And what you're doing with weather forecasting is they're looking at the spectrum, the high spectral resolution spectrum, and just immediately mapping that to a temperature and water vapor structure that they've seen before somewhere. Now, I will say that sometimes they're cheating a little bit. They're actually modeling things. And I think that's okay, but one of the things they've learned from things like AIRS, which was, you know, developed by JPL for the Aqua satellite actually flies with one of the MODIS instruments on Aqua, is they made all these predictions before it was launched. And then after it was launched, it's like, wait a minute, that's not what we thought it was going to be. And that's good. They learned something. So it's somewhat dangerous to base anything on just physical models. You want to base it on data and ground truth. Yes, absolutely. Absolutely. Oh, yes. Yes, yes, yes. Now I will say I'm not sure exactly what products are going to be released. I mean, eventually over time, there will be data like that. Certainly the raw data will be released, and so you'll be able to like do your own retrieval if you want to. But I think ultimately there will be products, you know, if you're looking for a specific chemical. Now, some chemicals are probably going to be hard to detect, even with the hyperspectral data, but some of them will be very easy to detect. At surf, yeah, right. Yes. Oh, that's interesting. Right? Right. Sounds like a glimmer paper coming in the future. Yeah. Yes. Yeah. 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 That's interesting. Yeah, I had not heard that, but I'm not surprised. I will say that, you know, things change, right? North and south of Point Concepcion, right? You've got, I mean, you've got the, you know, the great, you know, white sharks, you've got the killer whales, mostly north, although they're becoming more and more down south. And of course, we've got, you know, one of the great nurseries for great white sharks here in Manhattan. So that's right. Yeah. Right. Yes. All right. Yeah, sounds good. Well, so I will tell you, I used to do a lot of work for the government, and I never actually, I was still pretty junior at that point, so I didn't get to go on all the boondoggles, but there was one that the senior government scientists and contractors went on to Tonga to characterize ocean water. And while they were there, they just happened to do some fishing. Yeah, yeah, right. Yeah, I could probably go on that trip today, you know, but then I was, oh, you got to stay home and work on the data, you know. But yes. Yes, actually, and I'm glad you asked that question because you can even do that with multispectral data. Um, and that's another thing, another chart I took out of here. I would have loved to put every single thing in there, but if you look at, say, Veer's imagery or MODIS imagery of the Bahamas, you'll see very white areas. That is the bottom of the ocean. There's an area in the Bahamas known as the tongue of the ocean. And the bottom of that water, at the bottom of that water is white sand, and it's very bright, and the water is very clear. So you can see to the bottom. We used to do a lot of testing up there in the tongue of the ocean because it's a Navy test range for different things. So yes, and with hyperspectral, you can do even better. You can actually measure the depth with more accuracy. But unfortunately, you can't do that everywhere. So, you know, in optical oceanography, we talk about attenuation lengths. So typically, you can measure something like depth to 3 attenuation lengths. So for very clear ocean water, an attenuation length is basically 30 meters. That's pretty long. So 3 of those is like almost 100 meters. And I mean, can you believe that? Really, you could measure water that deep, but that's what the tongue of the ocean is. Now, as a counterexample, I'll describe Chesapeake Bay, okay, where the attenuation length is a millimeter. So, yeah, it's not very useful for measuring the depth of Chesapeake Bay. Yes. Oh, that's a great question. That is a heartbreaking question too, by the way. Yeah, so that's a problem. You know, for a geosystem, especially, it's hard to go north or south. You know, the Earth curves away from you, and there's just less, less solar irradiance that hits the surface of the Earth throughout the year. And so it makes it harder to get anything from high latitude. And of course, you know, depending on the season, it could even be dark, you know, at those latitudes for nearly all of the day. So all of those create challenges. And that's typically accounted for in the specification of an instrument like that. But the thing is that those are also very interesting parts of the world. I mean, we talked about how, you know, these high latitude areas are also very productive biologically. So there's a lot of interest in really knowing what's going on there too. Those areas may be best suited for the polar orbiting LEO satellites because even though, you know, a satellite like that will come over, say, the equator once a day, in the polar regions, it can come over every 90 minutes or so. So you're getting more frequent update rates. And so I would say that that's something that's better suited for the LEO satellites. Yeah, thank you. Any other questions? Yes, Chip. Well, I mean, I think the airborne data is still very useful. I mean, you know, ABRIS, you know, multiple ABRIS systems now, as you know, have been flying since the 1980s. And my favorite ABRIS project was when some of the wineries in the Santinez Valley, where my other home is near Solvang, asked me to use data to prove that some rogue winery was not actually in the right appellation, the San Rios appellation. So a very important use of hyperspectral airborne data. Yes, that's right. Yes, we had to validate it too, and they've made sure we did, you know, to show their gratitude for helping them. And so yeah, we used the airborne data, but we also used Landsat data too. So, you know, the key was having high spatial resolution, but we needed the spectral content of the hyperspectral to really say, yeah, believe it or not, that area over there really does have a distinctly different ecosystem, really, because there's both the climate, you know, is going up the Santinez Valley from Lompoc, and the fog only comes in so far regularly. I mean, it can be almost anywhere, but routinely it tends to stop at a certain place. The soil's different, vegetation's different. It's just different, and so that was a combination of space and air And the airborne systems will be used for validation. So I kind of talked about doing the validation in situ in the ocean, but and that'll be done. That'll be the most important validation. But you can still do things with airborne systems as well. Yes. Yes. So the different things they could do. My oldest daughter, who went to Berkeley and ended up with an NSF graduate research fellow in marine microbiology. So she's, basically educated in this field, even though she ended up as a patent expert rather than a mother. But she did a science fair project when she was junior high school, where she basically we went to SeaWorld actually and got some water, coastal water, literally from SeaWorld. And she monitored the growth of the phytoplankton in this water from SeaWorld. She also characterized it optically. So she had a transmissometer, which, simply measured the transmission of the water. She projected a laser into the water and measured how that transmission changed relative to the biological activity in the water. Now, if she were to do that project today, she might include other optical methods, like looking at the actual color of the water and actually doing some of the things we talked about here, but inside of an aquarium rather than in the ocean. So that's one recommendation. Yeah, I think I think the biggest effect we're going to see in coastal California is, the change in precipitation patterns. And so we've seen some weird weather. We've seen weird weather for a long time, right? But, we may see different changes in the patterns of weather, more extreme droughts, more extreme rainy years. We had a hurricane, right, that came up the coast. I was in San Diego when it hit. Nothing happened, but everybody was, freaking out because of the hurricane that was coming in. And we've had hurricanes before. I mean, there was one that hit Long Beach back in the 1930s. But so we're going to see changes like that. But I also think in response to these changes, we're going to see desalination of the ocean more and more. It'll have to become more affordable. But that's one way we can deal with it here in California. It's going to raise the price of water, but it's better than going thirsty, right? So, but I'll tell you, in Solvang, we've lived in Solvang for a long time, since the 1990s. And I have weather stations both at my house in Solvang and at the house here in Hermosa. A few years ago, we measured a temperature, still can't believe this, a temperature of 122 degrees at our house in Solvang. When we first moved to Solvang, in the summer, it would get up into the low 90s. Everybody would, oh, it's so hot, miserable. 122 degrees. I mean, even once. And the TV stations up there monitor, our weather station and many others. And they said, we don't know if we believe this or not. Some station near Solvang, reported 122 degrees. So, and I wasn't surprised to read, like maybe a year and a half later, about how that part of the Central Coast, the western part of Santa Barbara County, has seen more effective climate change than other parts of the state, the coastal part of the state. So it's still going to be relatively benign compared to other places that I'm afraid are going to become uninhabitable But yeah, Texas. Now, some would argue it's already uninhabitable, maybe for different reasons, but yeah, it's amazing what's going to happen. I'm in my 70s. Chad, what are you in your 80s now or 80s? Oh, spring chicken. But these changes, the big changes are going to happen after we're gone. Probably everybody is gone, but we're already seeing effects that look a lot like what people have predicted. So that's what I hear. Yes, they won't do it. And yeah, I don't want to get into that, but yeah, I was reading in the Wall Street Journal a couple of days ago about how you don't want to own a house in Florida right now and be trying to sell it. Yeah. Yeah, right. That's right. Yes. But when I pointed it out to somebody, that's what they said exactly. It's like, well, so what's different here? But yes. Wow. I know where Campo is. Yeah, I lived in San Diego for like 15 years. Yeah. Yeah. Yes. Right. So that's the thing. Yeah, I think we really have to be careful about, what we claim. There are trends. There's been extreme weather for a long time, as in forever. So it's a statistical thing. And when I try to explain it to people, I said and I think this audience might appreciate it. It's like traffic. Okay. I mean, it really is like traffic. Just slowly. I mean, I remember driving, in LA in the early 70s. And the 5 was just as bad then as it is now. The difference, though, is that now it's bad all the time. Back then, it was only bad for like a few hours, of the day. So it just kind of keeps changing. Yes. Oh, yes. Well, I did mention MIRIS, right, and OLCI. So those are European low Earth orbiting systems. Now, unfortunately, Europe decided not to go forward with their GEO ocean color system, and much to the heartbreak of Airbus, because they sold GOSI to the South Koreans at a very good price, thinking that would give them an advantage, for the European system. And it'll probably happen someday, but they've put it on hold for now. So I do think Europe will do that eventually. There is interest in the Middle East, actually, in ocean color and coastal water. Uh, the Persian Gulf is an area where there's a lot going on, sort of like the Gulf of Mexico, really. There's biological activity there, all sorts of human activity, obviously. I mean, the Indian Ocean is a very productive part of the world as well. The Indians actually tried to launch an ocean color system last year. I think it was about maybe a year and a half ago. I'm not sure I remember the exact date, but it failed at launch. They had worked on it for 20 years. In fact, I actually thought they had abandoned it, but I gave a talk in Germany at a place called EUMETSAT, which is a European weather satellite agency. It's in Darmstadt, Germany. And I said, there's this Indian thing, but that would be the first hyperspectral ocean color imager, except it's not going on. And some guy in the back of the room said, I was just in India last week. They said they're still working on it. I said, okay, well, we'll see. If it gets launched, then yes, it'll be the first. But Glimmer will be the first, because that one failed. Oh, yeah, go ahead. Oh, thank you. I was hoping somebody would. So what was the final score? All right. Oh, my. Oh, my. Oh, that's good. you know, and then Cleveland won too. So what I'm hoping, I really want the Yankees to come. That'll be forever. But I figure the prices of the tickets will go down if they play the Guardians. So, oh, but we'll see. All right. Well, that is very good news. Well, it's my pleasure. Thank you. Thank everybody online. Oh, I think you can.